Welcome back to the Deep Dive. We're the place where we take these, well, frankly, audacious ideas, the ones grabbing headlines, and we really try to apply some serious scientific thinking. Boil them down for you.
Get to the core of it.
Exactly. And today, we are going way off planet. We're diving into Elon Musk's proposal, which is, it's really monumental, to build the world's most advanced quantum computing facility.
Right, the Lunar Quantum Observatory, or LQO. That's a term the sources use.
And not just anywhere on the moon, but inside those permanently shadowed craters near the poles.
Yeah, it definitely sounds like something straight out of science fiction at first glance, doesn't it?
It really does.
But when you actually dig into the details, you look at the white paper they've put out, there's a surprisingly deeply rational and scientifically compelling argument behind it all.
Okay, so that's our mission for this deep dive, right? Get past the kind of wow factor, the spectacle.
Precisely.
Yeah.
We need to understand why. Why the moon? Is it just, a cool location? Or is it actually necessary for the next leap in computation? And what does this roadmap, this multi-decade plan for the LQO even look like? It's staggering.
All right, let's start unpacking that. And I think the place to begin is the physics.
Yeah.
The basic challenge, why does this idea even exist? Because building these quantum computers here on Earth is just, it's incredibly hard.
It really is. It's expensive, it's inefficient thermodynamically, you're fighting nature constantly.
And it all comes down to the qubit, right?
Yeah.
The fundamental unit of quantum information. It uses these two properties that are, well, notoriously difficult to keep stable.
Exactly. You've got superposition and entanglement. Superposition means the qubit can be like a 0 and a 1 at the same time.
Right.
And that's where the massive processing power comes from.
The exponential advantage.
Right. And entanglement. That's where you link two qubits. You measure one, you instantly know the state of the other, no matter how far apart they are. It's the spooky part, as Einstein called it.
Spooky and incredibly fragile. It seems like the slightest thing can just destroy that quantum state.
That's the perfect word, fragile. That delicacy is the absolute core engineering problem we face. The second a qubit interacts with anything in its environment, even a tiny vibration, a stray particle of heat, a bit of electromagnetic noise.
Oof.
Poof is right. It collapses. It snaps out of that superposition. And that loss, that collapse of the quantum information, that's what scientists call decoherence.
And decoherence is the enemy, the big bad.
It's the fundamental enemy of building large, reliable quantum computers. Everything we do on Earth is about fighting decoherence.
And Earth is just inherently noisy, isn't it? We've got heat everywhere, electromagnetic fields, the atmosphere itself, vibrations in the ground.
Constant noise.
Right.
So every quantum lab on Earth, whether it's Google, IBM, university labs, they're all locked in this incredibly expensive, complex battle just to push back decoherence for, fractions of a second, milliseconds, sometimes microseconds.
When you look at the effort involved, the massive lead shielding, the crazy vacuum pumps, the vibration isolation platforms.
It really makes you wonder, doesn't it? It
Yeah.
begs the question.
Yeah.
Why keep fighting this uphill battle against nature in such a noisy place when you could potentially relocate to somewhere where nature itself provides the solution?
Somewhere quiet.
Somewhere incredibly quiet and incredibly cold. The whole LQO idea is basically about saying, look, let's shift the entire engineering baseline. Let's start somewhere that's naturally 400 degrees Fahrenheit colder and has a vacuum that's orders of magnitude better than anything we can make here.
Okay, that sets the stage perfectly. Let's dig into how the moon offers that kind of, well, free engineering advantage. Right, so the number one enemy, as you said, is decoherence, and a huge contributor to that is heat. Thermal noise.
Absolutely. To get qubits stable, you need to get them cold. Really, really cold. We're talking fractions of a degree above absolute zero, the millikelvin range.
And on Earth, the way we do that is with these incredibly complex machines, dilution refrigerators.
Yeah, fridges they call them, but they're technological marvels. They use these mixtures of helium-3 and helium-4 isotopes to suck out heat and reach temperatures like 0.01 Kelvin, just incredibly cold.
But they come at a cost.
A huge cost. They're massive, they're extremely expensive to build and run, and they are serious energy hogs. The sources we looked at mentioned that a single one of these units can easily pull 20 to 40 kilowatts of power.
Just for one?
Just for one unit support systems. Now, imagine scaling that up to a proper quantum data center with hundreds of thousands of qubits. You'd need the power equivalent of a small town, basically just for the cooling.
Okay, so that's the Earth problem. Now, how does the moon flip this script? We're talking about these permanently shadowed craters, the PSCs near the poles, places like Shackleton Crater, Faustini.
Right, and the key is in the name. permanently shadowed. The sun literally never shines directly into the bottom of these craters because of the moon's low axial tilt. They're in perpetual night.
And perpetual night means?
Perpetual cold. Really deep cold. The baseline temperature of the lunar soil, the regolith, inside these craters naturally sits somewhere between 20 and 40 Kelvin.
Wow. Okay, let's put that in perspective. 20 to 40 Kelvin. That's around minus 400 degrees Fahrenheit, or minus 240 Celsius.
Yeah, it's colder than the surface of Pluto at its farthest point from the sun. It's just fundamentally deeply cold.
So, okay, 20 Kelvin isn't quite cold enough for the qubits themselves, right? You still need to get down to those millikelvin temperatures.
Correct. You still need the dilution refrigerators for that final tiny step down. But here's the absolute game changer. Nature does the vast majority of the cooling for free.
Ah, I see. It's like pre-cooling on a massive scale.
Exactly. That's the concept of the passive cryogenic laboratory. On Earth, you're burning enormous amounts of energy, just fighting your way down from room temperature, say 300 Kelvin, down to maybe 4 Kelvin, where the first stage of cryocoolers operate. Then you start the really hard work with the dilution fridge.
But on the moon?
On the moon, in these craters, you start your cooling journey at 20 or 30 Kelvin. That drastically slashes the energy needed for the dilution refrigerators, maybe by 80%, the sources suggest. And it significantly reduces their engineering complexity, perhaps by half.
That's a massive efficiency gain, something you just cannot replicate anywhere on Earth.
Impossible. It's a fundamental environmental advantage. Hashtag 2.2. Perfect isolation and stability.
Okay, so the cold is a huge factor, but it's not just the temperature, is it? It's the overall stability of the environment there.
That's critical too. Earth is constantly changing. You've got tiny seismic rumbles, changes in atmospheric pressure, thermal noise from, well, us, from human activity.
Right.
The inside of a PSC, it's incredibly stable. The temperature, deep in the shadow, varies by less than plus or minus 2 Kelvin, not over days or weeks, but over decades.
Wow. So you eliminate that whole problem of thermal cycling, things heating up and cooling down slightly, which must be a nightmare for sensitive quantum hardware.
It's a major source of noise and instability. So tick that box.
Yeah.
Extreme thermal stability.
And then there's the vacuum. We talked about fighting the atmosphere on Earth, pulling vacuums in chambers. How does the moon compare?
Oh, there's not even a comparison, really. Even the absolute best ultra-high vacuum chambers we build on Earth, like for particle accelerators at CERN or places like that, they're practically thick soup compared to the moon's natural environment.
Really? What are the numbers?
Well, a top-tier vacuum chamber on Earth might still have something like 10 to the power of 19 particles per cubic centimeter. That sounds like nothing, but
Compared to the moon?
the moon's exosphere, its very thin atmosphere, is down around 10 to the power of 4 particles per cubic centimeter.
Okay, wait. 1019 versus $10, there's 15 orders of magnitude difference.
15 zeros.
Mm.
It's an almost incomprehensibly better vacuum. And what that means is superior isolation for your quantum system.
How so?
Well, you basically eliminate convective heat transfer, heat moving around because of air currents, because of virtually no air currents.
Right, no air.
No humidity, essentially no dust floating around in the same way, none of those stray atmospheric molecules that can bump into your qubits and cause decoherence. The moon isn't just cold, it's incredibly clean, incredibly quiet, and ultra-stable on a level we can only dream of achieving on Earth.
It sounds like the perfect cosmic laboratory for keeping those quantum states alive for longer, maximizing coherence times.
That's exactly the idea. Longer coherence times mean you can perform more complex calculations before the quantum state collapses. Hashtag 2.3, low gravity and exotic experiments.
Okay, cold, check. Quiet vacuum, check. Stability, check. But the LQO plan also talks about leveraging something else. The moon's lower gravity, only 1/6 of Earth's. Now, how does gravity play into quantum computing? That seems less obvious.
Yeah, it's not immediately intuitive, but it opens up possibilities for specific types of quantum systems and experiments, particularly things like cold atom quantum computing and something called quantum metrology, which is basically ultra-precise measurement.
Cold atom computing, so using trapped atoms as qubits.
Exactly. And think about how incredibly delicate these setups are. On Earth, gravity itself, even tiny fluctuations in the gravitational field, or just the weight of the atoms, can introduce noise and instability into these traps.
But with only 1/6 the gravity.
The atoms can stay suspended in those quantum traps, those magnetic or optical traps, for much, much longer periods before gravity sort of pulls them out of alignment or causes issues.
Well, okay, so low gravity helps extend coherence times for those specific types of systems.
Precisely. It's another way to fight decoherence for certain architectures. But it's not just about making existing things work better. Low gravity actually enables entirely new kinds of experiments, things that are just too unstable or too short-lived to really study properly under Earth's full gravity.
Like what? The source material mentions some pretty wild stuff.
Yeah, things like exploring really advanced forms of entanglement, maybe probing quantum tunneling phenomena more deeply. And a big one is creating and studying Bose-Einstein condensates, or BECs.
BECs, those are the states where atoms get so cold they act like one single quantum wave.
Huh?
Right.
That's the one. They're macroscopic quantum objects. Incredibly fascinating, but also incredibly sensitive to vibrations, thermal noise, and gravity here on Earth. They just don't last long enough for detailed study.
So the moon, with its stability and low gravity, becomes this unique workbench.
Exactly. A workbench for exploring these exotic states of matter, pushing the boundaries of fundamental physics, and potentially enabling things like quantum sensors or clocks with accuracies that are just unimaginable today. Hashtag tag 2.4, natural radiation shielding.
Okay, let's address what seems like an obvious downside. Radiation. The moon doesn't have a global magnetic field like Earth does, or a thick atmosphere, so wouldn't radiation exposure be a huge problem for sensitive qubits?
You'd think so, right? More cosmic rays, more solar flares hitting the surface. But the LQO plan turns this potential negative into a positive, using the moon's own geography.
How?
The key is where they plan to build, not out on the flat, open plains, the mare, but inside these deep polar craters. They intend to build the facility underground or carve it directly into the massive rock walls of the crater itself.
Using the crater as a natural shield, like a bunker.
Precisely. That provides immense natural protection. You've got tens, maybe hundreds of meters of lunar rock and regolith overhead and all around.
And that shields the qubits from what, exactly?
Two main things. First, the constant background shower of high-energy galactic cosmic rays. And second, the big bursts of radiation from solar flares, these sudden storms from the sun.
And we know those can affect quantum computers on Earth.
Absolutely. The sources mention that existing quantum processors, like the ones Google operates, actually show measurable spikes in their error weights during periods of high solar activity, even with all the shielding they have on Earth.
Wow.
So by using the moon's own rock, essentially burying the facility, you get natural shielding that's equivalent to, say, 2 or 3 meters of solid lead.
Okay, that's serious shielding.
It provides this incredibly quiet radiation environment, ensuring that computers can operate continuously with high fidelity, basically regardless of what the sun is doing. It adds another layer to that perfect isolation advantage.
All right, this is where the conversation takes a bit of a turn, isn't it? From the pure science of quantum computing to, well, resource economics on a cosmic scale.
It really does, because the LQO isn't envisioned just as a standalone science lab. It's designed to be the seed, the catalyst for a whole new lunar economy. And at the heart of that economy is a very specific isotope, helium-3.
Helium-3, we mentioned it earlier in the context of those dilution refrigerators, for getting down to ultra-cold temperatures.
Exactly. He, as it's written, is absolutely crucial for that final stage of cooling to the millikelvin range needed for many types of qubits. It's vital for the ultra-low temperature research that underpins quantum computing.
But the problem is, it's incredibly rare on Earth.
Extraordinarily rare. We only manage to gather, maybe a few thousand liters globally per year, and most of that comes as a byproduct from maintaining nuclear weapons stockpiles or from certain nuclear reactions. It's very difficult and very expensive to get your hands on significant amounts.
Okay, scarce on Earth. But the moon.
The moon is a completely different story. Because it lacks that protective magnetic field and thick atmosphere that Earth has, it's been constantly bombarded by the solar wind for billions of years.
And the solar wind contains helium-3.
Loads of it. And over geologic time, that helium-3 has become embedded, trapped within the top few meters of the lunar soil, the regolith.
So how much are we talking about, if it's scarce here?
The estimates are just staggering. The sources suggest the lunar surface holds somewhere between 1 and 5 million tons of helium-3.
1 to 5 million tons. Compared to a few thousand liters a year on Earth.
It's an unbelievable abundance, a true lunar motherlode. And this potential resource completely changes the economics and the logistics of the LQO.
How so? This is what the sources call the dual revolution, right?
Exactly. It's revolutionary in 2 major ways. First, for the LQO itself. If you can extract HEU on the moon, you can supply the dilution refrigerators right there.
Making the facility self-sufficient in its most critical coolant.
Precisely. No need for complex, expensive resupply missions carrying tiny amounts of heat all the way from Earth. It solves a massive logistical problem.
Okay, that's the first revolution. What's the second?
The second one is potentially even bigger, looking beyond the moon. Helium-3 is widely considered the ideal fuel for advanced fusion reactors.
Fusion power. The dream of clean, limitless energy.
That's the one. Heli-fusion is attractive because the reaction itself doesn't produce neutrons, meaning it creates far less radioactive waste and structural damage to the reactor compared to other fusion fuel cycles, like deuterium-tritium that most current experiments use.
So establishing a lunar heat supply chain doesn't just power the quantum computer's cooling.
It could potentially fuel a multi-trillion-dollar clean energy industry back on Earth, or power future deep space missions and settlements. It connects the LQO directly to solving humanity's long-term energy needs. It's a massive economic justification. Hashtag tag 3.2. Engineering the power solution.
Okay, extracting helium-3 sounds incredibly valuable, but let's get back to the practicalities of the LQO itself. You've got this billion-dollar computer sitting in a pitch-black, super cold crater. How do you actually power the thing?
Yeah, that's a huge engineering puzzle, isn't it? You need reliable high power, but you absolutely cannot have your power source dumping heat into the cold environment you chose precisely because it was cold.
Right, it seems like a contradiction. How do they solve it?
It relies on clever use of the lunar geography and some advanced energy transmission tech. The plan is to put the power generation outside the crater, up on the crater rims.
Where there's sunlight.
Exactly. Some crater rims near the lunar poles are in near perpetual sunlight. So the idea is to install large arrays of high-efficiency solar panels up there. The sources mention gallium arsenide, GATA's rays, which are very good in space environments.
Okay, so you generate constant power on the sunlit rim, but then you have to get that power down into the permanently dark, cold crater where the LQO is. How do you bridge that gap without just running a giant heat-generating extension cord?
Right, you can't just run standard cables. They'd lose too much energy as heat and ruin the thermal environment. So they proposed two main methods for efficient long-range transfer. First, power beaming.
Beaming? Like wirelessly?
Essentially, yes.
Yeah.
Using highly focused microwave or laser beams to transmit the energy from the solar arrays on the rim down to receiver stations located near the entrance of the LQO facility inside the crater.
Wow. Okay, that covers a long distance into the crater. But once the power reaches the receiver, you still need to distribute it within the LQO complex, right? To the computers, the life support for maintenance bots, the Hato refinery, maybe?
Correct. And again, you can't use regular wires because of the heat they generate through electrical resistance. Even tiny amounts of heat are unacceptable near the quantum processors.
So what's the solution for local distribution?
This is where superconducting cables become absolutely essential. These aren't your typical copper wires. They're made from special materials. The sources mention possibilities like niobium titanium alloys that, when cooled below a certain critical temperature, conduct electricity with practically zero resistance.
Zero resistance means?
Zero heat loss from the cable itself. And conveniently, the ambient temperature inside the PSC, that 2040 Kelvin range, might actually be cold enough or nearly cold enough for some types of superconductors to operate efficiently.
Ah, so the moon's natural cold helps make the power distribution feasible too.
It's another Thernergy. You use the ambient cold to enable lossless power transmission right up to the sensitive equipment, preventing the power system itself from becoming a source of thermal noise. And a really elegant integrated design concept. Hashtag tag 3.3. The LQO systems and modular design.
It sounds incredibly complex, but also very thought through in terms of integrating all these systems. Let's picture the whole setup. It's not just one building, right? The sources describe it as highly modular.
That's key for deployment and potential expansion or maintenance. It's conceived as a collection of interconnected modules. At the absolute core, you have the cryogenic chamber complex.
That's where the qubits live.
Exactly. Buried deep within the crater walls for maximum shielding and thermal stability. This houses the actual quantum processors, the dilution fridges, and probably associated physics labs for experiments.
Okay, then linked to that, you've got the power infrastructure we just discussed.
Right. The surface power network up on the sunny rims, with the solar arrays and then the power beaming systems and the superconducting cable grid connecting down into the crater.
And crucially, you need the resource component.
Absolutely. You need the helium-3 extraction and refinement facility. This would likely be located somewhere more accessible, maybe on the crater periphery, where robotic mining vehicles can operate more easily in sunlight. It needs to be highly automated, constantly scooping up regolith, heating it, and separating out that precious heat isotope.
Okay, so cryo complex, power network, heat refinery. What else?
You need the communications link, a quantum communication array. This would likely be a sophisticated optical telescope system designed specifically for transmitting entangled photons over vast distances, forming that quantum internet link back to Earth or other space assets.
And finally, you need ways to maintain all this complex gear.
Yeah, the maintenance modules. And given the environment and the latency issues we'll discuss later, these would rely heavily on autonomous robotic systems and drones for inspection, repairs, and component swaps. Human intervention would be minimal and likely reserved for major upgrades or catastrophic failures.
So this isn't just a dream. There's actually a proposed timeline, a phased approach to make this Lunar Quantum Observatory a reality. And it seems to tie together advances in quantum tech with the build-out of actual space infrastructure.
Yes, the sources lay out a concrete three-phase roadmap. And it's ambitious. They're targeting the kickoff for Phase I deployment around 2030.
2030, that's really soon. What makes them think that's feasible?
A big part of it is the assumed availability of new super heavy lift rockets, like SpaceX's Starship. You need that kind of massive payload capacity to the moon to even begin contemplating landing the necessary hardware.
Okay, so assuming the rockets are ready, what's Phase I? It runs from 2026 to 2030.
Right. Phase I is all about robotic pathfinder and site qualification. It's the essential prep work, the due diligence before you start pouring billions into construction.
Makes sense. What are the main goals?
First, pinpoint the absolute best crater. Shackleton and Faustini are prime candidates, but they need detailed surveys. Characterize the thermal environment precisely, map the regolith composition, especially confirming the concentrations and accessibility of helium-3. Is the resource really there in the quantities they expect?
So scouting, basically. What needs to be demonstrated technologically in Phase Y?
Couple of key things. They need to test the autonomous construction robots. Can they navigate the terrain, dig, manipulate materials effectively? And critically, they need to validate the power beaming technology. The sources say they need to prove they can reliably beam at least 100 kilowatts into the dark crater.
Why 100 kilowatts specifically?
That seems to be the threshold calculated as the minimum needed to power the initial cryogenic systems and the first set of robotic operations for the next phase. It's a crucial go-no-go milestone. And they'd also want to return some regolith samples confirmed to be rich in heat.
Okay, scouting, mapping, tech validation, and the price tag for just this preparatory phase.
Estimated at around 4 to 6 billion US dollars.
4 to 6 billion just to scout the location and test some robots? Wow. Okay, what's next? Phase 2.
Phase 2 runs roughly from 2030 to 2035. This is the construction and initial deployment phase. Now you actually start building the core facility inside the chosen crater and installing the first quantum systems.
So this is where the LQO starts to actually compute.
Yes. The main goal here is to get the first operational quantum processor up and running. It might be relatively small by future standards, maybe 10 to 100 qubits, but it needs to be functional and stable in the lunar environment.
And alongside the computer.
They also need to establish the helium-3 refinery pilot plants, start actually producing the coolant on-site, and initiate that first quantum communications link back to Earth, proving the secure connection.
What are the big technical challenges here? Installing superconducting qubits inside cryo chambers built into frozen moon rock sounds tricky.
Immensely tricky. You're dealing with specialized materials, probably niobium titanium alloys for the qubits, needing extreme cold and vacuum, integrating them into chambers carved into the crater walls, all done largely by robots in a hostile environment. The engineering complexity is enormous.
And the cost reflects that, I assume?
It does. The estimate for Phase 2 jumps significantly to $15 to $20 billion.
Okay, so by 2035, maybe we have a small functioning quantum lab and a heat pilot plant on the moon. What's the final stage, Phase 3?
Phase 3 is projected to span from 2035 to 2045. This is the expansion and industrial hub phase. This is where the LQO goes from being a pioneering outpost to a full-scale strategic facility.
Selling everything up.
Massively.
Yeah.
The computational power target jumps to over 1,000 stable qubits. That's getting into the realm of truly powerful, error-corrected, utility-scale quantum computing. The kind that can solve problems currently intractable for even the biggest supercomputers.
And the helium-3 production.
That also scales up dramatically, moving from a pilot plant to industrial-scale extraction. The target mentioned is at least 10 tons per year.
10 tons of heat a year. Is that enough to actually start impacting that fusion energy market we talked about?
It's certainly enough to begin supplying demonstration reactors and proving the economic viability of the lunar resource. It makes the whole fusion connection much more tangible.
And the cost for this decade of major expansion.
This is the biggest ticket item, an estimated $50 to $70 billion for Phase 3 alone.
Wow. So adding all that up, Phase 1 to enter a total projected investment to get the full LQO operational by 2045 is roughly
Around $74 billion.
$74 billion. That is
Yeah.
just an astronomical sum of money.
It is absolutely a monumental figure. But the sources providing these numbers are quick to put it in context. They compare it to other massive, decades-long, bleeding-edge technology projects, things like building out a global network of exascale AI supercomputers or the multi-billion-dollar budgets for projects like the ITER fusion reactor experiment here on Earth.
So it's huge, but maybe not unprecedented for a project promising paradigm-shifting capabilities.
That seems to be the argument. The question they pose isn't just, can we afford it, but what is the cost of not having this capability? What's the return on investment, not just in dollars, but in scientific discovery and strategic advantage? Hashtag 4.2. Managing earthly constraints, logistics, and latency.
Okay, $74 billion phased over decades. It sounds incredible on paper, but we need to bring it back down to Earth, or maybe down to the moon's surface. Let's talk about the really hard constraints. Logistics, for one, the cost of just launching all that hardware.
Is immense. The sources estimate the transport costs alone could account for something like $18 billion of that $74 billion total. Just getting the stuff there is a huge chunk of the budget.
And beyond the cost, the moon is just a terrible place to work, isn't it? We talked about the vacuum and cold being advantages for the computer, but for maintenance, how do you fix incredibly delicate, super-cooled quantum instruments when they're surrounded by abrasive, clingy moon dust in a hard vacuum?
You've absolutely nailed the core operational nightmare. That lunar dust, it's not like dust on Earth. It's pulverized rock, sharp-edged, electrostatically charged due to the solar wind and UV radiation. It gets everywhere, sticks to everything, and it's highly abrasive.
So if that gets into the cryogenic chambers or onto optical surfaces or into qubit connections,
It's game over. Immediate, catastrophic failure. Decoherence goes through the roof.
right.
So managing the dust is arguably the single biggest physical engineering challenge for long-term operation.
What are the proposed solutions? Because you can't just send up astronauts with feather dusters every week.
No, definitely not. The whole concept relies heavily on extreme automation and advanced materials science. They talk about needing things like specialized self-cleaning surfaces for equipment,
Self-cleaning, how?
and even more critically, deploying electrodynamic dust shields. These are fascinating. They basically create oscillating electric fields around sensitive equipment or seals. Since the lunar dust particles are charged, the electric field actively repels them, preventing them from settling and accumulating.
Okay, so high-tech dust mitigation. But what about repairs? Things will still break.
They will. And this brings us to the other massive constraint, the human element, or rather, the lack of it, due to communication latency.
Right. The moon isn't that far in cosmic terms, but light still takes time to travel. What's the round-trip delay?
Roughly 2.5 seconds, about 1.25 seconds for a signal to get from Earth to the moon, and another 1.25 seconds for a response to come back.
2.5 seconds. That doesn't sound like a lot in everyday life.
It doesn't. But imagine you're trying to remotely operate a delicate robotic arm to replace a faulty qubit chip cooled to millikelvin temperatures. Or you're trying to diagnose a rapidly cascading system failure in real time. A 2.5-second lag between your command and seeing the result, or between an alert and getting telemetry data. It's an eternity. It makes direct interactive control impossible for anything complex or time-sensitive.
So the entire LQO operation, it can't be run directly from Houston or anywhere else on Earth.
Essentially, no. Not in a hands-on, real-time way. The human command loop is just too slow.
Which means?
It means the LQO must rely overwhelmingly on autonomous AI systems located right there on the moon.
AI has to run the show.
Pretty much. If humans can't react fast enough, the onboard AI has to handle almost everything. Managing the complex cryogenic systems, monitoring qubit stability, performing error corrections, scheduling computations, diagnosing problems, deploying repair bots. All of it, autonomously.
What percentage are we talking? How much is AI versus human oversight?
The source material throws out a figure that autonomous AI might need to handle 90% of the day-to-day operational tasks. Humans back on Earth would be more in a supervisory role, setting high-level goals, analyzing long-term data, planning major upgrades, and intervening only when the AI flags a problem it can't solve or requires strategic direction.
Okay, that that feels like a really critical point. You build the most powerful computer imaginable, stick it on the moon, and then you have to trust an AI to run 90% of it because of the speed of light.
It's a massive reliance on AI robustness and reliability. It raises huge questions.
Mm.
What happens if the AI fails? What are the backup systems? How do you update or patch that AI securely with a 2.5-second delay? If the power beaming gets interrupted or if dust does manage to degrade the AI sensors, is the whole $74 billion facility suddenly bricked, dependent on software running autonomously almost 400,000 kilometers away?
That's a tension right there. Building this incredible tool, but having to relinquish direct control over it. It's fascinating and honestly a bit unnerving. Hashtag TAC 4.3, economic modeling and funding.
And speaking of unnerving things, let's circle back to that $74 billion price tag. How on Earth or on the moon do you actually fund something of this magnitude? It's far beyond typical science budgets.
Right. It can't just be NASA or ESA writing a check. What's the proposed funding model?
The sources suggest it has to be a complex blend, moving beyond traditional government funding. A major component would likely be public-private partnerships, PPPs.
So government agencies working with private companies.
Exactly. You'd see space agencies like NASA, ESO, maybe others, partnering with the big aerospace players like SpaceX for launch and logistics, and potentially tech giants like IBM, Google, or specialized quantum computing firms for the actual hardware development and integration. It mirrors how things like the International Space Station were funded, sharing the cost and leveraging private sector expertise.
Okay, PPPs make sense. But $74 billion is still a lot to pull together. Is there anything more innovative in the funding plan?
Yes, this is where it gets really interesting, moving into the realm of financial engineering, tailored for massive, long-term, high-risk, high-reward projects. The plan involves trying to pull future value forward to fund the earlier, expensive construction phases.
How do you do that?
Through creating specialized financial instruments. The two main ones mentioned are lunar bonds and data futures markets.
Lunar bonds. That sounds futuristic. What are they?
Essentially, it would be debt issued by the governing body of the LQO project. Maybe this LQA we'll talk about later. Investors buy these bonds, providing upfront capital. The bonds would be backed by the future expected revenues generated by the moon base.
Future revenues like?
Primarily two things. First, the potential multi-trillion-dollar market for helium-3 if the fusion energy connection pans out. And second, guaranteed access to the LQO's unique computational power.
So that ties into the data futures market idea.
Exactly. Imagine large corporations, pharmaceutical companies, material science firms, AI developers. They know they'll eventually need access to the kind of powerful, stable quantum computation the LQO promises something maybe unattainable on Earth.
So they could essentially pre-purchase compute time.
Precisely. They could buy contracts today guaranteeing them a certain amount of cold compute cycles on the LQO years or decades down the line. This creates a data futures market. Companies invest heavily now, effectively helping fund the construction, in return for securing priority access to this unique computational resource later.
That's clever. It shifts the funding model significantly.
It does. It moves away from relying solely on taxpayer money or government grants, and towards treating the LQO as a strategic industrial investment. Companies aren't just funding science. They're buying a stake in the future of computation itself, betting that the moon's advantages will deliver capabilities that give them a massive competitive edge.
The risk is obviously huge, but the potential payoff, exclusive access to potentially world-changing compute power, is equally massive.
Exponentially higher, potentially. It's a gamble, but one with potentially civilization-altering stakes.
Okay, so if they manage to build this thing, fund it, get the AI working, the LQO isn't just going to be sitting there crunching numbers for drug discovery, right? Its location and capabilities have much broader strategic implications, particularly for communication.
Absolutely. It's positioned not just as a supercomputer, but as the ideal central hub for a future space-based quantum internet.
A quantum internet, using entanglement for secure communication.
That's the core idea. We mentioned the extreme isolation and vacuum on the moon. That environment is perfect for generating and transmitting delicate quantum states, like entangled photon pairs over vast distances with minimal decoherence.
Better than trying to do it from Earth or even Earth orbit.
Much better. On Earth or even in low Earth orbit, you're constantly fighting atmospheric absorption, scattering, turbulence, and background noise that can easily destroy the entanglement needed for quantum key distribution. QKD?
QKD, that's the technique for sharing fundamentally secure encryption keys, right?
Exactly. By generating entangled photons on the moon and beaming them down, you can establish theoretically unhackable communication channels. The moon's stable vacuum platform acts as a perfect relay point.
So you could link Earth, the moon base itself, maybe future Mars missions or orbiting stations.
With encryption keys distributed via entanglement, making the communication immune to eavesdropping, even by other powerful quantum computers. It creates an ultimate digital shield for interplanetary communication.
Secure against the very technology it enables. That's quite something.
It is. And beyond secure communication, there's the metrology aspect again. The same stability that helps qubits and entanglement also benefits atomic clocks.
Codes on the moon.
Lunar-based optical clocks, operating without the subtle gravitational fluctuations or seismic noise of Earth, could achieve unprecedented accuracy. The sources mention potential 1018 accuracy.
Which is useful for?
Ultra-precise navigation throughout the solar system. Fundamental physics tests, potentially redefining global timekeeping standards back on Earth. It becomes a fundamental piece of cislunar and interplanetary infrastructure.
When you take all these pieces together, the computation, the communication, the resources, it really seems to fit into that larger narrative, particularly Musk's vision of humanity becoming multi-planetary, diversifying our technological base.
It absolutely does. The LQO isn't just a faster computer in a colder place. It's framed as potentially the first off-planet knowledge engine, a fundamental shift in where and how humanity does its most advanced thinking and discovery.
Accelerating everything.
Potentially, yes. Stable, large-scale quantum computation could unlock breakthroughs across the board, designing radically new AI algorithms, accurately modeling fusion reactions, discovering novel materials and catalysts, developing personalized medicines based on quantum simulations of molecules, even running real-time, high-fidelity simulations of Earth's climate or complex ecosystems. The sources talk about it enabling a quantum civilization.
That's a bold term.
It is, but it reflects the potential scale of impact. And the economics projected around this vision are frankly mind-boggling. We talked about the helium-3.
Right, the potential $10 trillion fusion energy industry it could fuel.
Exactly. That alone suggests, according to the sources, a potential greater than 10x return on the initial $74 billion LQO investment. That's the kind of number that makes investors and governments pay attention, despite the risks.
So the argument is that the infrastructure needed to support this, the launch systems, the lunar robotics, the cryogenic tech, the quantum hardware itself,
Becomes strategically vital. The sources use the term quantum cold chain, suggesting this supply chain for ultra-low temperature quantum systems will be as fundamental to the 21st century economy as the semiconductor supply chain is today. It's about repositioning global technological and industrial leadership. Hashtag 5.3, geopolitics and governance.
And that brings us squarely into the geopolitical arena. If controlling the LQO means controlling the future of computation, secure communication, and potentially fusion energy, this isn't just science anymore, it's power politics.
Without a doubt. The nation, or the consortium of nations and companies that successfully builds and operates the LQO, gains an almost unimaginable strategic advantage. It could very well become the 21st century equivalent of nuclear superiority.
Having the ultimate code-breaking machine and the ultimate uncrackable communication network all in one place.
Exactly. It completely reshapes the global balance of power. It elevates the strategic importance of the moon from symbolic flag planting to controlling a critical technological high ground.
Which inevitably raises some really thorny ethical and legal questions. We touched on the funding, but who actually owns the moon's resources? Like those millions of tons of helium-3. Is it finders keepers?
That's a huge unanswered question under current international space law, like the Outer Space Treaty. It prohibits national appropriation, but is vague on resource extraction by private entities.
And how do you prevent this incredible technological leap from just widening the gap between the haves and have-nots, making global inequality even worse?
These are critical concerns that the proposal itself seems to acknowledge need addressing before major construction begins. You can't invest $74 billion without some framework for governance.
So what kind of governance structure is proposed?
The sources suggest the need for a multilateral approach, advocating for the creation of a dedicated international body. They float the name Lunar Quantum Authority, LQA.
And an LQA, what would it do?
The idea is it would be maybe affiliated with the UN, perhaps modeled on international scientific organizations like CERN, which manages the Large Hadron Collider, or the IAEA, which oversees nuclear safety and technology.
So, ensuring fair access.
That would be a primary mandate. ensuring that access to the LQO's computational power is available on fair, non-discriminatory terms to all signatory nations and research institutions. Also, establishing safety protocols, data sharing principles, and generally preventing the facility from being monopolized or used purely for aggressive military purposes.
And what about the environmental aspect on the moon itself? Mining He involves digging up huge amounts of regolith. Could that damage other important lunar resources like water ice?
That's a major concern, especially since the water ice is also concentrated in these same permanently shadowed polar craters, the cold traps. The ice is vital for future human presence, for life support, for rocket fuel.
So the LQA would need an environmental role, too.
Yes, the sources emphasize the need for a sustainability charter as part of the LQA's mandate. This would set strict rules for hake extraction to ensure it doesn't destabilize or contaminate these crucial ice deposits. It's about balancing the immense technological and economic potential with the long-term preservation of the lunar environment for future generations. You have to manage the gold rush carefully. Hashtag Tag 6. Conclusion and provocative thought. So if we try to pull all these threads together, what we're looking at with the Lunar Quantum Observatory proposal is, on one hand, a really elegant, almost necessary scientific solution. It tackles the fundamental physics problem of decoherence by literally moving the lab to a place where nature solves most of the problem for you.
Leveraging the moon's extreme cold, that 20 to 40 Kelvin baseline, its near-perfect vacuum, its stability, and even its geology for radiation shielding.
Exactly. But achieving that requires this absolutely enormous technological and financial undertaking.
Mhm.
We're talking a $74 billion price tag, funded through complex public-private partnerships, and maybe even things like lunar bonds and data futures.
And it hinges on overcoming massive logistical challenges, particularly the pervasive lunar dust, and crucially, relying on highly autonomous AI to manage the facility because of that inescapable 2.5-second communication delay.
And the payoff isn't just faster computation. It's the potential for a secure quantum internet, a new multi-trillion-dollar fusion energy economy fueled by lunar helium-3 and a fundamental shift in geopolitical power.
The key numbers to keep in mind: that 20 Kelvin natural advantage, the potential millions of tons of helium-3, the $74 billion cost, and that 90% reliance on AI. It's a calculation of immense risk versus a potentially world-altering reward.
It really is.
There's an analogy that comes to mind. If you think about the 20th century, maybe its technological pillars were the transistor, enabling the digital age, and the satellite connecting the globe and opening up space. Perhaps the defining technologies of the 21st century, as this proposal suggests, will be the qubit and the crater. It signals this potential shift, moving humanity's most advanced technological capabilities off-planet. So, we want to leave you, our listeners, with a final thought to chew on, something that really stems from that latency issue we discussed.
The 2.5-second gap.
Exactly. We established that because of that delay, the LQO, humanity's most powerful potential computer, would need to be run mostly by autonomous AI. Maybe 90% autonomous, human supervised, but the AI acts.
Right.
So here's the question. If our most advanced, most capable computational system is built on the moon, operating in perpetual darkness, largely running itself, what does it truly mean for us, for Earth-based intelligence, when our ultimate thinking machine operates in a place we can observe, we can communicate with after a delay, but we cannot truly directly control in real time? What are the implications when our smartest creation operates autonomously, silently, in the dark, 250,000 miles away?
That's definitely something to think about.